Okay, good. So thank you very much. Thanks for the kind invitation. It's a pleasure to be here in person. Sorry for the online people who don't enjoy this feature of being able to travel again. I would like to tell you about experiments which we do at ETH Zurich, in which we couple a quantum gas, a Bose-Einstein condensate, to an optical cavity. And this combination of two ingredients gives rise to long-range interactions between the particles. And that's our artistic view on what goes on. So you see like two atoms, these red marbles here, which are interacting via the exchange of photons. These are this yellow stream. And this is then giving rise to long-range interactions and the self-consistent dynamics of the system. Now, what I would like to show you in this talk is what dissipation means for the system. And the reason is that these photons are captured, confined in a cavity, but this cavity is not perfect, so photons can escape. And you can ask what happens to my many-body system in presence of this dissipation. So let's start simple. We have a many-body system. It's closed at the moment and there are no interactions. So we need to add interactions to make it of any interest. And if we have these interactions, then you can imagine that the system will have different ground states, which depend on the strength or on the kind of these interactions. And so you can imagine that we have two different orders here. And there's a control parameter which we can tune lambda, and there's a critical value at which this many-body system will switch from one order to another order in its ground state. So this is something which is well studied so far. And now the question which I would like to ask is, what happens if we now add dissipation to the system? Obviously, if we only add dissipation, then everything decays to the vacuum state. We lose all the photons, we lose all the atoms, and that's a boring situation. So we need to replenish this dissipation now by a drive, and we end up at a driven dissipative system. Okay, and now the question is, what remains from the physics which I've talked to you about in the closed part if we go to this open version of a many-body system? Okay, one thing which you might imagine is that this critical point gets slightly shifted due to the presence of dissipation, because dissipation and drive, this can give rise to additional fluctuations or a change of fluctuations, so this can influence your critical point. If you think of these fluctuations, then you might also think of second-order phase transitions where you have universality, so you have critical exponents which are describing this phase transition, and in presence of dissipation, this exponents can change. And that's something which we studied quite a while ago in our system, and saw that there's actually a change of the critical exponent if the system is open. Now, in this talk, I would like to show you that more dramatic things can happen, like you can have dynamics which emerges due to the presence of dissipation. So this can mean that you don't find a stationary state anymore for your driven dissipative system, but you enter a non-stationary evolution of the system, like limit cycles or chaos, even synchronization. What I would like to show you in this talk is that we discovered that there can exist some kind of a pumping mechanism where you have a geometric pump which produces the center of mass of the atoms to walk in space. And this is only due to the presence of dissipation. That's the first part of my talk. And then the second part, I would like to show you these phase diagrams here, which we theoretically and experimentally studied and saw that the presence of dissipation is fundamentally changing the shape of this phase diagram. Okay, all this is done on the platform which I introduced to you, a many-body cavity QED. So it's a quantum gas coupled to a cavity. You see on the left-hand side what we imagine as a concept. In the middle, you see what we imagine as a implementation. So we put our rubidium-87 Bose-Einstein condensate into a high-finesse optical cavity, illuminate the atoms from the side with a standing wave laser field, which is far detuned from atomic resonance. Atoms are not excited electronically, they just scatter the photons. And then these photons can eventually end up in the resonator. And on the right-hand side, you see our imagination, what this could be inside. If you like this kind of system, there's a recent review article which I co-authored, so I would ask you to have a look at this one. There are different experimental platforms. Now there are with us 4 bosonic systems, and now since 3 days there are 2 fermionic systems. So this article from Shanghai just appeared in Science. Okay. If you want to capture the physics, you start with a single particle description. That's our single particle Hamiltonian written in the rotating frame of the pump. So you see eta A is number of photons, and we have here the energy difference, delta C, the detuning between the pump and the cavity frequency. We have the kinetic energy of the atoms. We have the pump lattice potential, so the atom will experience this potential of the pump. We have the cavity lattice potential, so you see only if there are photons inside the cavity, then you will have a potential along the cavity axis. And then we have this interaction term, which is given by the interference of the field scattered into the cavity and the pump field. So this, if you think of the interference, gives the rise to a checkerboard lattice which the atoms are feeling. Again, this goes with the amplitude of this coherent field inside the cavity and with the square root of the pump lattice potential. So now originally this is
what keeps the atoms tight?
What I neglected here is indeed a trap. So the atoms are trapped externally in a dipole trap.
So dipole trap. So optical from the cavity standing waves, and this no, it's not enough.
We don't. So we could use just the cavity field to trap the atoms, but as you see, originally the cavity is empty, so we would lose the atoms in this direction. So what we do is that we confine the atoms in an external 3D harmonic trap.
And you don't switch off.
Which we don't switch off during this experiment, so it's a trapped experiment the whole time, which can have its problems at the end.
So once again, what does the interaction potential mean?
So this interaction potential is giving rise to long-range interactions between the particles. So you can imagine that
it's the same photon mode which is felt by all the particles.
Exactly, all particles feel the same one, so it's a global range mean field interaction. So what I also neglected here is, well, it's still the single particle Hamiltonian, but the atomic interactions will come only later. There's collision interactions. So originally the system is in the normal phase where you see that there's no photon inside the cavity, and in order to populate the cavity you need to look at the competition between 2 energy scales. One is this interaction potential through which the atoms can minimize their energy if photons are scattered into the cavity, because then they are populating this checkerboard lattice and they are confined in this checkerboard and minimize energy because it's a attractive potential for the atoms. On the other hand, you have the kinetic energy, which counteracts this, because this means you need to bend your wave function, which the atoms don't want to do. However, if you ramp up this pump power at some critical pump value, you will have the transition from a normal phase to a superradiant phase. And at this point, this interaction potential has 1. That's the single particle Hamiltonian. And here you see actually the potential in case of the superradiant phase. So you see it's a lambda periodic potential with this funny shape, which is nothing else than a cut through this checkerboard lattice. Now going to a many-body description, you are sandwiching this single particle Hamiltonian together with the atomic interactions, so the collisional interactions in between your field operators, and this gives you an idea of the many-body system. What's crucial here for us is we can integrate out the light field, and if we do so, we have an effective long-range interaction between the particles, in addition to the short-range collisional interactions between the particles. So some time ago, we looked at this on a lattice model, so in a Hubbard regime. Now, in what I'm going to talk about today, we are not on a lattice, but it's a free space or a trapped system at which we're looking at. Okay, in this case, we can expand our field operator very simply, saying we have a Bose-Einstein condensate which occupies a single momentum state, p equals 0, which is this blue dot here. And then the scattering is transferring atoms from that state into a symmetric superposition of 4 other states, which are given by the scattering from the pump into the cavity and vice versa. So these are 2 levels. It's like a 2-level atom, if you want. So we can map this system in a simplified way onto a spin. It's a macroscopic spin, and so that is why we can actually map this system onto the Dickey model. So that's a paradigmatic model which is describing the interaction between n 2-level atoms in a single electromagnetic field mode, and that's something which we did simulate with this system. Okay, now we look at the experiment. This is at the heart of the experiment. You see these 2 pieces of glass. These are our highly reflective mirrors. This is 1 Swiss franc. So this is a comparison in size and not in price. And these mirrors are approached to 180 microns. So it's a very narrow gap. And in this gap, we are producing our Bose-Einstein condensate, 100,000 atoms of rubidium-87 at a very low temperature. Here you see a time of flight image in between these 2 mirrors. Okay, this is buried in an optical chamber. The chamber is buried in optics, and this is how the experiment looks. Now, this is the first data which I would like to show you. We ramp over time the transverse pump power. That's shown as a dashed line here, this black dashed line, with which we illuminate now the atoms. And you see that although we are sending photons onto the atoms, this blue line stays at 0, so the atoms are not scattering photons into the resonator. This is because the kinetic energy is winning at the moment, and we need to have strong enough atomic interactions, or this cavity-mediated interactions, such that the system turns into a super radiant phase, which you can see here. So at this point, we have photons inside the resonator, and you see that we have these additional momentum peaks being occupied. So the atoms acquire now this checkerboard lattice and scatter efficiently photons into the cavity.
Sorry. Can you also distinguish whether the light photons are coherent with the light coming out or incoherent?
So we can measure the properties of the light field, as I will show you in a second. We can stay in this phase for quite some time, and then if we ramp down again the pump field, we can go back and retrieve our Bose-Einstein condensate. So all this is like more or less staying in the ground state of the system. As you asked, can we analyze the properties of the light field? Yes, we can. We can not only look at the photon number, which we would do with a single photon counter doing clicks, but we can use a heterodyne detector and measure both quantities of the light field, which means we have access to the phase of the light field. And you see here that it's ill-defined if you have no photons, and it's locked to a certain value if it's in the organized phase. This is something which we can make use of to analyze not only the density modulation, but also the fluctuations of the system, so we can actually see excitations in the spectrum of the photons. We can also use this access to the phase to distinguish which of the 2 possible patterns of this Z2 symmetric system of this checkerboard lattice is occupied. So by ramping in and out of this self-organized phase several times, we can see that the corresponding value for the phase shown below here has a difference of pi, and this corresponds to nothing else than being on the even or the odd sides of the checkerboard lattice. So it's this dashed or the solid line and this potential, or if you would like to define an order parameter, you would take the overlap between the atomic wave function and this lattice, which is then 0 in the normal phase and acquires a positive or negative value in the organized.
Here is periodic pumping of this periodic driving of the pump, or what are you doing there?
So in the upper plot here, we are just driving in and out of the phase. So it's the pump which is increased and decreased, such that I can show for you that we have different realizations.
Here, why the total number is going down, just because it's longer time.
And here it's longer time, and experimentally, I think at this point we did not have the line filter, which means we had too many resonant photons on the laser.
Okay.
So the lifetime is longer than this usually. Okay, so this is was my introduction to those long-range interactions and how the system can self-organize. Now I would like to build up step by step to then arrive at this geometric pump.
You don't have dynamics of the system in a way because of strong interaction or because of time scale or both.
Which kind of
you show us then your atoms are somehow organized in a pattern, right? In the slides, but you don't have coping between the different nodes.
Okay, yes. So you
special dynamics you don't show us. Is it because the interaction wins and it's just an image of a static picture, or it's just on the time you're looking at time scale where the dynamics, how people do it typically in video. Yeah, so really, sorry, not two, the exact different state. So is it?
Okay, I would say the time scale at which you could imagine to find excitations or to find physics is the time scale of recoil. So it's the time scale at which atoms can move due to atomic recoil. And this is something which is within the time which we observe here. So now you say, I just see a flat line, which is only partially true because there's noise on top of this flat line. So I would say I showed you some dynamics, but since we are looking at an averaged observable, we are looking at 10 to the 5 particles which do dynamics. So I think most of it cancels out. But it's a good point. And so, for example, when we spectrally analyze this light field while the system undergoes a phase transition, we indeed see side bands which take place at the soft mode frequency. So we can see how the first excited mode softens when we go closer to the phase transition, and then it approaches zero actually. And this tells me that indeed we see the dynamics of the system going on, but not on this level of resolution which I showed to you here. So in this data which we've analyzed, it was, I think, a difference in 5 orders of magnitude of the photon level of the coherent field versus the incoherent field, which I didn't show you, but I'm happy to show it later.
I guess maybe also it didn't use the fact that you are in a single mode regime, both for the cavity and the atomic mass.
Yes, so you.
If you would have more mode of the photon field,
yes.
I guess the special dynamics would be.
Yes, so you could imagine that if you have competing modes here, then you have spatial dynamics which goes on. And so we have another experiment, which I'm going to introduce you now, is where we have 2 cavities which cross actually. And there we saw how the system evolved from one to the other. And then the experiments on multimode cavities, like from Benjamin Leff at Stanford, who is then going to the extreme case of almost infinite number of modes and trying to see then phonons in the system. Okay, so now we are still with few modes. This apparatus here is a different one than before, and I'm just showing this picture because I'm proud of it. So it's inside the vacuum chamber, and you see that we have lots of small optics in this vacuum chamber. If you look from top, then you see it's 2 pairs of mirrors of cavities which cross. But for what I'm going to show you, we are again back to a single cavity and 1 retro-reflecting mirror. So if I draw the modes for you, then you see that we have here a mode crossing at the center, and this is where the physics takes place, and this is how you should imagine it. Important message, we have tilted the cavity. So everything is a bit skewed now, which is important for the experiments, but this makes also the data look a bit different. Okay, we can take a phase diagram of the system. Colored means we detect photons out of the cavity. For the rest, it's the same experiment as before. So we can change the detuning delta C between pump and cavity, and you see that if you are farther detuned, you need more pump power for the system to self-organize. Okay. And if you take a time of flight image, we see this characteristic momentum peaks, and we understand all of them. And that's it. It's just skewed with respect to the data before. So now we go to repulsive potentials. So the atoms are organized for the attractive potentials such that they maximize scattering into the cavity mode, and this gave them a potential. Now, if you go to repulsive potentials, the atoms are avoiding the light field. So you're blue detuned with respect to the atomic frequency. Atoms are pushed away from the light field, and you can ask whether in this situation at all the system is willing to self-organize. because the atoms avoid the light field. Indeed, it is possible, and this is due to destructive interference. So the atoms are scattering lots of light, lots of photons into the cavity, and they make it in a way that they arrange themselves such that the destructive interference between the pump and the cavity field makes them nice positions for them in space. So this is possible, and we can now look at the difference between the red detuned case, so the attractive potentials, and the blue detuned, which I'm showing you now. And you see here that the phase diagram has changed. So if you now go to larger pump powers in this blue detuned regime, you see that this phase is not extending to infinite pump powers, but it decays again here. And if you look at the time of flight images, you see that only 2 of those modes seem to be macroscopically occupied. So if I take the Fourier transform and would look in real space, I don't find a checkerboard pattern, but I find a stripe pattern. Okay, so I have now 2 different phases, and I can study what goes on here, and we can try to understand why this phase looks different. For this, we go back to the single particle Hamiltonian, and what you need to know is that the pump potential Vp and the cavity potential U0, they depend on 1 over the atomic detuning, so they're sign sensitive. Now, if I plot for you the potential of the pump, then for the attractive case, you see that there are minima, and in this minima, the atoms will accumulate. So the atoms in the ground state are shown here as this gray line. And if I now also plot the interaction potential, then you see that the atoms are coupled to a state with the same parity. So it's a symmetric coupling. That's different if you go for the blue detuned case, because now you see that this pump potential is flipped in sign. So if you stay with the same coordinate system, your atomic wave function is shifted by lambda over 4, which means now that if I add the interaction potential, the atoms are in the ground state are coupled to a state of opposite parity.
You mean interaction between us?
I mean cavity-mediated interactions between the atoms. Yes.
Good. Yeah. Not like that. Yeah,
it's the effective interactions between the atoms mediated by the light field.
Yeah.
Okay, now if I plot this potential which arises, then you see that it's this funny double well potential. So it's like a dimerized potential which the atoms are experiencing. It means that the atoms are coupled to the p-band. Okay, so we can look at first the attractive case. You see that that's the dispersion relation, energy versus the quasi-momentum. Atoms are sitting in the Q = 0 state initially, then the Raman coupling by pump and cavity couples them to this state, which is in the same band, so same parity. Different for the repulsive potentials, where we are coupling to the p-band. Okay, now let's look at what happens to these bands if I ramp up this pump potential. First thing is, what you will see is that there are 2 minima evolving at these points, which corresponds to the mode softening. So that's where the system would like to acquire its density modulation, and it's like a rotonization, so roton mode softening. Second thing which you will see is that the band gap is opening because we are loading the atoms into a band. Okay, so this is what happens for the repulsive case, and as soon as this minimum hits the 0 line, we will have self-organization. Good, let's look at the blue detuned case. Again, you will see that we have minima evolving. Again, you will see this band gap opening. But now what happens is that at some point we have self-organization, but then these roton-like minima are growing slower than the band gap is opening. So for deep enough lattices, the system is going out of this self-organized phase again, and this is the reason why this phase diagram has this funny shape. Okay, so seems like we understood what goes on here. Now, I would like to show you what happens if you want to combine these 2 phases. So the idea was it would be nice, well, as you know, that the 2 structures are different, and can we induce a structural phase transition between this stripe and this checkerboard order. Okay, to do so, we kept our field being repulsive, so we stayed on the blue detuned side, but needed to have a mechanism which induces this checkerboard order. And we do this by having both a running and a standing wave pump in the experiment. So you see here that we can write this pump field as the sum of two counter-propagating fields. And if they are imbalanced, then you see you have a standing wave component, and then the excess field is a running wave, which you can describe as a cosine plus a sine. It goes in this direction, exactly. Okay, what does it mean? We go back to our single particle Hamiltonian. Not much changes for the blue detuned case. You see they have this funny potential with the double wells. All what changed so far is that this amplitude is a bit smaller. But this did not take into account this running wave component, which is connected to the sign of this field. So this is something which we need to add here. And you've seen that now you have the cosine and you have the sine appearing, which means you again flip a sign. And this tells you that in addition, you can have this possibility of the other type of potential. Also very important, what you can see is that the lower line, the sine, is coupled to the imaginary quadrature of the cavity field, while the upper one is coupled to the real quadrature of the cavity field. So it's just a phase in the light field, and this is something we can detect because we have the same phase sensitivity. Okay, so if we run the experiment, measure the phase diagram with these imbalanced pumps, we indeed find characteristic features of both phase diagrams. So you see this tip, which we know from the repulsive side, and you see this extended phase, which we know from the attractive side. And indeed, if we take time of flight image, we see that there are two different atomic structures, and we can distinguish them nicely. Now, I told you that imaginary quadrature and real quadrature are occupied, so we can measure the phase of the light field, and you see that it clearly switches by pi/2 if you go from one phase to the other. So this is confirmed. Now, we did this to study this first order phase transition between these two structures. And we do so by just ramping up the pump power and looking in time what happens to the light field. Okay, that's shown here. As a function of time, I plot for you in the lower plot the phase of the light field, which should jump from 0 to pi/2. And in the upper plot, I show you on a polar representation the light field. So you have the real quadrature on the horizontal axis and the imaginary quadrature on the vertical axis. And the radius gives you an idea of the amplitude of the field. Now we run the experiment and we let the system undergo this phase transition. And then you indeed see that the system jumps by pi/2 in its phase. We see that the amplitude is changing, which corresponds to nothing else what we saw in the phase diagram. And we see this ringing of the signal. And now if you think of a first order phase transition, then you might understand what goes on. You have this global minimum, which turns into a local minimum, and then the system spills over in the free energy landscape. And then you have a relaxation in this newly evolved minimum, which we can indeed observe in our experiment in real time.
Sorry, what is the turn and break symmetry between the two minima? Because I thought that the Hamiltonian you wrote also in the previous slide when you had the other puzzle was still kind of symmetric. Yes,
so you need to think of two different symmetries here. Okay. So I show you the two different phases in red and green, which correspond to the two different patterns. One is stripy in red and one is checkerboard-like in green. That's one type of thing which is broken here, and this corresponds to these two minima. At the same time, each of those two phases have their own Z2 symmetry breaking, because you can shift everything by lambda/2. And this is
goes beyond the Giga model kind of.
Exactly, yes.
Okay.
Okay, and what you also see in this lower plots is that's a real space representation is the unit cell of our lattice, which evolves here. And you see that while the system undergoes this transition, there's a shift of the center of mass position of the atoms. So it's something which one calls the polarization, this modern theory of polarization. And you see that it's shifted in space. Okay, wrapping up this part, we saw a phase transition, second order one going to this organized phase, first order structural phase transition with this ringing on the other side. Now, I promised you that we wanted to look at dissipation, and now we're at the point where we can do it. Now you know everything. So we need to have the regime where the dissipative processes given by kappa, that's the rate at which dissipation takes place in our system, cavity decay rate, is on the order of the coherent processes, which is delta C, the tuning between pump and cavity. So we need to not operate this in the limit delta C much larger than kappa, but being roughly equal. We can do so, change our parameters, and you see that we still find the characteristic features of these two phase diagrams, but they look now a bit noisy. So we were not so happy at the beginning, and we had to average many of these shots, and then you see that it looks much nicer because we averaged, but still there's something going on, and you see that there's this wide region where the phase seems to be ill-defined. Okay, so perhaps we were too fast. We should look back at what happened in these noisy traces. And if you now look at a single row here, then you see that the phase of the light field is doing a step-like evolution in time. So for a certain parameter regime, and this is just, you see over time, we are ramping up the transverse pump power, but we could also stop at this intermediate regime. And in this intermediate regime, the system starts to continuously evolve its phase. It seems to oscillate here. Now, this was something which caught our interest. And if you look now in this polar plot representation, you see that we are encircling here this minimum several times. And this is nothing else than the phase wrapping and slight modulation of the light field amplitude. Writing down equations of motion for the atomic field and the light field inside the cavity, you see that these are coupled, of course, self-consistent. You can define mode integrals, which is the overlap of the atomic wave function with either the sine pattern or the cosine pattern. And if we solve those in a Gross-Pitoyevsky-like simulation, then we see indeed a feature which looks very similar to our experiment. We see this stepwise evolution of the phase. And now, if I plot for you the mode integrals, then you see that the system is constantly swapping between the cosine and the sine part. And if you think of cosine and sine, which are interchanged, then this is nothing else than a transport in space. Okay, so that's a first indication of a pump. Second indication, if you think of the pictures I'm showing you here, then this polarization is changing continuously. If you go in the circle and you see that that's an indication that the system might actually move its atoms out of the in real space position. In order to nail this down, we installed an in situ image. So we are now looking with a camera, not in time of flight, but we're looking in real space of the atoms while this experiment is taking place. And we see that the center of mass of the cloud is displaced as a function of this number of phase wraps. So it's indeed a transporting mechanism which takes place here.
How do you know the position of the center of mass of the measure?
So we take an absorption image of the atoms and we fit the center of mass.
Okay.
But you see that you need quite a good resolution in order to find this, because it's the scale is here lambda, so it's on a micron scale.
So these variables P and Q, what are they again?
P and Q are the real and imaginary quadrature of the light field. So the left-hand side is only observations which we find from the light leaking out of the cavity.
Okay.
The right-hand side is atomic observables.
Right. Okay.
And you see that it's as a function of this phase wraps, so and not as a function of time. So it's actually the evolution of this phase, which is correlated to the position. Okay, so if I call this a pump, then you might say we know pumps from cold atoms. So there's geometric pumps, there are topological pumps, and they're usually built by having two lattices, a short lattice and one lattice with a doubled period. And if you now take an external device which slides the two with respect to each other, then these minima are doing some jungling like this, which effectively changes the tunneling J1 and J2 continuously and the side offset between neighboring sites. And now you need a two-dimensional parameter space, or at least two-dimensional, which you encircle this singularity in the middle. And if you do so, then your quantum gas can undergo transport. So this is what was shown in the experiments by Takahashi with fermions and by Bloch with bosons. And there's a nice relation to the Archimedean screw, where you also have some external handle, which you have a periodic modulation, a periodic deformation of your potential, which leads to a linear translation of a system. Okay, but you see those two examples here, or those three examples, they always need some external force or external motion, which is imposed onto the system such that it moves in space. That's different in our system, and that's what surprises us, that we don't have any external time-dependent drive. We just apply a CW field, but the dissipation of the system gives rise to this instability, which then gives rise to this pumping mechanism. Okay, that's something.
I think that the drive is there, but the periodicity is self-produced by the light field. It's
self-induced periodicity, exactly, yes. So now, as I promised you, we can look at the frequency spectrum of the photons. And you see that this spectrum, when the system comes into this pumping phase, is shifted. So there's another frequency component. And this is something you can understand if you solve the eigen equation of the system. Then you see that there are two eigenmodes corresponding to the sine and the cosine part. And they coalesce at an exceptional point where you have then synchronization between those two modes until it splits again. And so there's one mode which is amplified, that's the one which we see, and one mode which is damped, that's what we not see. Okay, and this is something which you might know from photonic systems, but also we had another experiment where we coupled spin and density to the system and could observe some similar dynamics. Okay. Question?
Just maybe
as far as I can see, the fundamental difference between what's happening here and the pumping observed in the experiments that you referred to is that pumping is dealing fundamentally with a gapped system. So the system of particles there are fermions, and there is a gap to the excitations in that fermionic system. That's hugely important for the operation of the pump. There are no excitations, and all pumping happens through virtual processes, not through any real processes. There are no real processes responsible for pumping. In your case, it seems more like there is a drag of your system, self-induced drag of your system due to the real processes happening in it, because this is a bosonic system, it is gapless. So particles actually move around in a physical way to induce pumping. So that might be a slight difference between the two.
No, I completely agree with you. So we are not in a limit where you have fermions, or as in the case of Immanuel Bloch, where you had a mod insulating state. Effectively fermions. Our case is the situation where we have bosons. The other thing which you could remark here is that you could question how adiabatic this process is, because the time scale is now given by the system itself. It might be not completely adiabatic.
It's not adiabatic by definition, because if your system is gapless, then adiabaticity is broken at any pumping rate. So yeah. It is a different kind of fish.
Yes, I completely agree with you that it's not the same, but for us it was a surprise that we can observe self-induced pumping in this.
What you find here is a new phenomenon. It's not
exactly.
It is something completely new.
Yeah. Okay, so this was second part. Now I come to the last part, which is about this new phases. And for this, we can take one step back and say, in general, if I would like to study different dissipative systems, metal-light interacting platforms are good to use. And you see that there's a plethora of different platforms from solid state to atomic physics, quantum optics. And what they all share is that they're usually described by a paradigmatic atom-light coupling. So you can trace back all of the physics at the end to the Rabi model, where you have a spin which is coupled to a single mode of a light field. Now you know that you can, in the not strong coupling case, you can go to the rotating wave approximation, then you end up with the Jaynes-Cummings model. And if you go for many atoms or many two-level systems, then you have the Dickey model, which I presented to you. And if you do here the rotating wave approximation, you have the Tevis-Cummings model. So you throw away again the energy non-conserving terms. Now, what we looked at was the interpolation between Dickey and Tevis-Cummings model. So you see that by having this lambda x and lambda y, we can tune in how many of the counter-rotating terms are actually present in the system and how many are cancelled. Okay, and this is interesting if you want to look at the influence of dissipation. That's why I show this here. So that's the phase diagram of the closed system. You see the phases are colored if you have a photonic field in the system. So either the real part or the imaginary part, A plus A dagger or I times A minus A dagger. And if you are on these limiting cases where either lambda is 0, you have the pure Dickey model. Otherwise, you are somewhere in between. And you can also look at the phases of the light field, and you see that either the real or the imaginary quadrature are occupied. They seem to expel each other. If you are right on this diagonal line here, then you are in this Tevis-Cummings limit, where the system doesn't have a Z2 symmetry, but a U1 symmetry. Okay, that's the closed system. We go to the open system and solve the Langevin equations. And then you find that the phase diagram looks very different. Because now this phase, which is non-organized, where there are no photons inside the system, is extending actually to infinite coupling strengths. And that was surprising to us, because even infinitesimal dissipation destroys this organized phase if you go to infinite coupling strengths. In addition, you see that this multi-critical point has split up, and you see that there are now new coexistence regions. So it's a first order phase transition, which is induced here, it seems.
Nice.
Yes, please.
Sorry, I just was wondering, how do you model, like, what is Ullin-Bladian here? Just
it's the standard decay mechanism of the cavity.
okay.
Just photon losses.
Sorry?
Photon losses.
Just photon losses, exactly, not more.
Yeah, I see. Thank you.
You had the same question? Okay, very good. What you also see is that both phases now are not exclusively either real or imaginary in their light fields, but you have that in both cases, if you are away from this 0 line, from lambda equals 0 lines, you have that both quadratures are occupied. Okay, we set out to experimentally implement this scheme, and for this we needed to enlarge our space a bit. So we are not coupling only to density, but we are also coupling to spin. So you see here our two states are now given by two Zeeman states of the atoms, and we can split them and control the splitting with a magnetic field. And we have one state in which we prepare the atoms in this BEC, and then we switch on a laser, which is coupling those atoms to the other Zeeman state via a Raman transition, where we take a photon from the laser and a photon is then scattered into the cavity mode. So you see that our atoms are again illuminated by an additional laser field. And then if this frequency of the laser field is such that energy is conserved, then we can end up in this lower state, which is modulated in space. Now we can add, well, if we don't do anything more, we just pump the atoms over there. So what we do is that we add a second field, which is then closing the circle, and we can go back to the initial state. Okay, and if you think of this closing the circle, that means that you can actually reuse the photons which you scatter into the cavity to go back to the initial state, and this realizes something like the Dickey model. But in addition, you saw that we have these decay processes, and these photons can be lost out of the system. And this is what I mean with the open system. Okay, so now if you think of this Hamiltonian, then you see that we have the control parameters, which are the amplitudes of this blue and red light field, eta r and eta b. The sum of the two are like the lambda x, which I had before, so this coupling parameter to the real quadrature, and the difference between the two is the coupling parameter to the imaginary quadrature. And that's what we can make use of now in our experiments. First, let's look at the decay limit. So delta eta equals 0, which means we have balanced pumps, and we have a perfect balanced situation in this Raman coupling scheme. And in this case, the decay physics should happen. We have the ground state initially, there's a critical point, and you have an excited state which softens, and at the critical point you go into the superposition of the two. Okay, now what about the dissipation? Well, we can write down the dissipation rates, and you see that they scale with the power of the pump fields. So they are balanced for this situation where we have balanced pump fields. So as many excitations decay from the excited state to the ground state as from the ground state to the excited state. This changes if we go away from this decay limit. So now we allow for an imbalance between the two fields. And you see that we still have a normal phase in the superradiant phase, but you see that we have decay processes which are imbalanced now. And this imbalance can be so strong that at some point this superradiant phase ceases to be present, and this is this dissipation stabilized normal phase. Okay, that's our measurement. We ramp up over time the two pumps shown as solid and dashed black lines, and we record the photons, and we find a phase diagram which looks very much as the theoretical prediction, and we can even plot our predictions on this and are more or less happy with the comparison. We found hysteresis in the system, so that's the other indication which I've shown you on the theoretical plot before. And we had also access to the excitation spectrum. So similarly to before, we can analyze the frequency of the photons, in this case, after exciting the system. And you see, if you go along the decay line, you see that we find here in this plot B, this mode softening and then superradiance. And if we go along these other lines, you see that this becomes more strongly damped, and at some point the superradiance has vanished. And this is a comparison again with theory, where we solve for imaginary and real part, and you see again good agreement between these decay rates and our experimental data.
Sorry, just one question. I'm confused. You call it dissipation, stabilized normal phase. This eta bar, I understood they control the ratio between rotating and counter-rotating, not the dissipation.
Yes.
So is it why this dissipation that is somehow giving you this normal phase? Well, why you would say dissipation is responsible for the disappearance of the superradiance? Maybe I missed that one. I guess yeah, this.
It's here.
Yeah.
So it's you see in this blue box, you see that the dissipation rates of going from one state to the other, they depend on the power of the two beams. And this is corresponding to delta eta or eta bar.
Okay, so you increase the height. Okay.
Yeah. Okay, so and this is a summary of this part. We observed first theoretically, then experimentally, that we find this dissipation stabilized normal phase, which is only there due to the dissipation rate of the system. Okay, I had a similar problem as you, Felix, that I read the title and felt a bit uncomfortable because I don't have any impurities, and what I did is to do dynamics in complex quantum environments. But I'm now saving my skin, and I show you one plot about impurities. So that's even mentioned in the abstract of the workshop. Take a Bose-Einstein condensate of 100,000 atoms and put it into a cavity. Do on-resonant probing, look at the Tavis-Cummings model. You find a big splitting, which is shown here. It's gigahertz large. That is due to the coupling between all these atoms and the cavity mode. But now you prepare some of the atoms, not in this state, but you prepare a few atoms in another hyperfine state. And this other hyperfine state is also coupling to this cavity mode. And if you are in the single atom strong coupling regime, you will find a splitting of your resonance. And so in this case, like 1% of the particles is in this other hyperfine state, and we can detect them. And in consecutive measurements, we actually found, I would say, order of 10 to 20 particles on top of 100,000 particles in the other state. So we do have access to this quantity, and you see that it's non-destructive measurement. So this is one measurement round here, and you see that we use only a few photons to detect these few particles. So this impurity is actually cooled by the environment, and at the same time, we can detect the presence of these particles. Okay, with this, I would like to show you the people who were involved in this experiment. So there are two teams, one with this crossed cavities and one with the single cavity, and we have former group members which contributed, and we have our theory collaborators. And I would like to thank all of them kindly, and I would like to thank you for your attention.
Good. Can I ask a question? Yeah. So I'm curious about this part where you have oscillation and self-sustained oscillation in the light field. There was a lot of discussion about breaking of time translation invariants, time crystals. So do I understand correctly your model, your experiment, you don't have somehow any explicit time dependent in your problem, right? Is that correct? So, and now the question is, how much would you say your setup is in the quantum regime? What I mean is that this kind of decay model, when you go, since you have long range mean field interaction, you end up sort of having dynamical equation that has been since a long time known to have limit cycle, right? For a quantum problem, for like, you know, if you are in the quantum regime, this is not clear. So I wonder whether, where would you sit yourself? Is it mean field theory capturing all this, or no, quantum fluctuation are important? Can you say something about that?
Yeah, thank you very much. So we're also wondering whether if we should interpret this in terms of time crystals. And if you watched what happens on the archive, then there's the group of Andreas Hemmerich, which were recently publishing about their time crystal, which is a system which is very similar, although in their case, they were driving it periodically, and then they found
that is very different from your setup.
Yes.
Here you have a complete homogeneous in time problem, and then it starts oscillating.
Yeah. So in this sense, or taking their definition of what a time crystal is, I would say, or would claim that what we show is the breaking of continuous time crystal.
Yeah.
At the same time, my personal feeling, perhaps this should be off the records, I don't know, is that this is all very ill-defined, or not, well, we are here in a workshop, so I would like to hear your definitions of what a time crystal is and what it means that it's dissipative and an open system. And is it there only due to dissipation? Yes, I would say so. So then it's a dissipative time crystal. And it's robust, yes. Is it many-body? Arguable. You pointed to the specifics that it's a all-to-all interaction. It's mean field. True. At the same time, you could argue, well, the system has its underlying S-wave collisions. So it is actually, there are collisional interactions. We can put it into a strongly interacting regime by adding a lattice. Yeah, and that's probably what we should do.
That would be very.
So I guess that's the way to go to understand this this phenomena. And well, we didn't want to put the name time crystals because it's, we don't know what it means.
Yeah, I guess.
At least some people define time crystal as a periodic driven system which demonstrates periodic behavior at a different period than the driving period, and no dissipation. So these are the two conditions for it to be called the time crystal. Because there are lots of dissipative systems that spontaneously break time translation symmetry. For example, a bucket that you fill with the water until it tips over and returns to the initial position. You fill it with water again, and so on. It's a so.
Yes, I agree with you. And again, that's the reason why we didn't want to enter there. Originally, the time crystals were imagined to happen or to exist only in closed systems. Then there were theorems which told us it doesn't exist. Then it seemed like the community was expanding and saying, well, then let's look at the open systems. But then I would argue, well, already the water bucket or the child in a swing, any parametric driven system shows a subharmonic response. Okay, then you would need your strong interactions to
suppress dissipation. That's the
yes.
second part of the definition nowadays.
But then there's also the definition by Berislav Buka and Dieter Jaksch, I believe, about dissipative time crystals, which are there only due to the presence of dissipation, not despite. So yes, it's a discussion.
Can I ask another question about this? So beside the names and so on, so it oscillates. Can you remind me? Is it your system has a symmetry? What is the symmetries of this? You mentioned some Z2. Can you remind me?
Yes. So we have
phase is free.
The phase is free to run.
Okay.
But if you think of a free energy landscape, then there are 4 specific points in which there are minima, okay. And they correspond to the different patterns. We have 2 Z2 symmetric pairs, one being the stripe pattern with its Z2 symmetric pair, and one being the checkerboard pattern with its Z2 symmetry.
Okay.
Are there questions from the online people?
May I ask a question?
Sure.
It's basically it's a very simple one. I didn't completely understood the role of like interaction between atoms in the first experiment. Could you just very briefly remind me?
Okay, so I would say all these experiments would look very similar if there would not be interatomic interactions. So if the collision interactions would be negligible, well, we wouldn't have a superfluid, but still we would have well-defined momentum states, so this would not change a lot. If you now add interactions, you will find, or we found that the critical points of these phase transitions are shifted, and we can quantify this. But I would say all of the phenomena which you've seen here would survive in the same way. Now there's work, for example, by Francesco Piazza, who was looking at the blue-tuned regime which we were investigating. And this work was actually the trigger for us to do it, because he proposed, or he showed, that there should be a time evolution on the system, like an oscillatory state, which he then connected to the collisional interactions and to vortices which are created in the system. So there are phenomena which are expected to be there due to these interactions. But what I've shown you here was not due to the interactions. What we had done previously, as I told during the talk, is that we have a lattice model. So we have a 3-dimensional optical lattice in which we load our atoms, and then this is a Hubbard model, a Bose-Hubbard model, and then we add the cavity around, and this gives rise to long-range interactions. And then we found phases like a charge density wave phase and the mod insulator on top of what you've seen here, and there certainly these interactions are dominant or are competing with the other scales which are shown. And now a natural extension of what I've shown you today would be to go into a lattice.
Yeah. Sorry, just to continue on this, in order to see something like that, you will need to go in a regime where
where the cavity resonance, cavity shift is of the order of dissipation?
Yes.
Okay, that is the key somehow to, okay.
Yes, to have this dissipative effects important, we need for this pumping mechanism and also for the other case.
The previous experiment you have done with the lattice,
It was not in that regime because we were always far away from the cavity resonance. Okay. You're the chair.
Well, I'm not the chair, but I see that people continue disappearing online. Do we have any other questions? Okay, if not, then we are stopping our recording.